All right, so we are going to talk about resonance and harmonics. Resonance, it says here, the vibration at the natural frequency produces resonance. So we have an image here of some tuning forks. If we take this first tuning fork and we strike it, it will then vibrate. Now, what frequency does it vibrate at? That is going to depend on the structure of the tuning fork. But every tuning fork has its own vibration pattern. And we can actually see this in things like a string or a rope that's held really tight so that it's in a straight line, or if you were to thump the top of the desk or the leg of the chair, they're all going to have some natural pattern with which they vibrate, which is then going to create a sound. So we hear the different noises when we strike the different objects because of that natural frequency. So it says when the natural frequencies match, and here specifically we are talking about of our tuning forks, then they will resonate. So in the image you see that the tuning fork on the far left is initially struck and put into motion. It creates a vibration. That vibration pattern is then going to cause vibrations in the air molecules, and those air molecules are going to spread out throughout the room. So the tuning forks that we have on the right, you can see, are all slightly different. They have different sizes to them. They're going to have different wavelengths, which is going to in turn cause them to have different frequencies. So you can see that this tuning fork here in the middle is illustrated to show that it is also in motion. What this tells us is that these two tuning forks are identical. They are the same frequency. So when the first tuning fork was struck and sent out its vibrations, that vibration pattern perfectly matched the vibration of the tuning fork in the middle. And so as a result of that, it also began to vibrate. Notice that the other two tuning forks are not in motion because they do not match the frequency of the first tuning fork. So resonance is a condition that exists when the frequency of a force applied to a system matches the natural frequency of vibration of the system. So this idea of resonance is what is causing that second tuning fork to go into motion. Because those waves have matching frequencies, when the first tuning fork is put into motion, its vibration pattern matches the vibration pattern of the second tuning fork, and so that creates the resonance. At the same time, if I were to strike both tuning forks, they both are going to emit the same sound, so we're going to hear the same pitch from both of them. So when I strike them both at the same time, then their waves are going to build up constructive interference to create not a different pitch. It's going to be the same pitch. It'll be the same note, but it will simply increase the amplitude, which, if you recall, is just the intensity of a wave. So when we are dealing with sound, increasing the amplitude would make the volume louder. Okay? All right, so a standing wave is a wave pattern that results whenever we have a wave that is sent forward, it hits some sort of boundary or barrier, and then is reflected back onto itself. In this picture, what we see is that we have an initial wave that was sent, and in this case, it's showing us well, I guess it's not showing a direction, so we're going to assume that the initial wave was sent forward to the right. Now you can see over here it hits some sort of boundary or barrier, and so that is going to cause the wave to be reflected back in the direction that it came from. So on this illustration, they put the reflected wave as a dotted line so that we could differentiate between the two. So not only does the wave get sent back, but it also becomes inverted. So when the wave returns, instead of returning on the positive x-axis that it came in on, it's going to return on the negative, and so we end up with this mirror image of the first wave. And so this overall picture that we see here we call a standing wave. So there are two parts to a standing wave. We have the nodes, which are going to be, as I like to explain it, the nodes are going to be the points of no amplitude, right? So right here, these are all our nodes. So on this particular image, you can see we have 4 nodes. The antinode would be the opposite of that. Instead of having no amplitude or our points of total destructive interference, we're going to have complete constructive interference. So my antinode is the opposite of no amplitude. And so this is where we are going to have our maximum amplitudes. Now my string or my wave, whatever type of material is being oscillated here to make the standing wave, is physically only present in one place at a time. But if we were to disrupt the molecules, and if you visually think of plucking a string or vibrating a string, this might be easier to visualize. But if we create that disruption or disturbance at a high enough frequency, it will then reflect perfectly back on itself like the image that we see. And so it may appear to the physical eye that the string is present on both positive and negative side of equilibrium simultaneously, which we know is not physically possible. So if you notice in this illustration, we see that they have marked 3 antinodes. Now, in actuality, the antinodes would be here because this would be the physical location of my disturbed molecules at this particular moment. On the image, they actually placed them so that we had our middle antinode marked here. As long as you understand that it is the location of the maximum displacement, then that would be sufficient for identifying your antinodes. Notice that we would count this as 3 antinodes in this illustration. Harmonics is an idea where we create a standing wave. This allows us to understand what frequency is needed in order to create a wave, or I should say, we first need to figure out what frequency is needed in order to create a standing wave. And then if we simply increase our frequency at that increment, so if we say that our first frequency to create a standing wave is 6 hertz, then every multiple of 6 is going to create an additional standing wave. So our harmonics is a series of frequencies all based off of whatever that very first frequency was. So it says standing waves on a vibrating string. This is what we're looking at. And again, we can analyze the motion of a string to get a better understanding of what is happening within the molecules of things that maybe we cannot see. So here we can talk about vibrating an actual string. Maybe think of a guitar or some sort of stringed instrument. So the fundamental frequency is the special name that is given to the very first harmonic. So on the illustration, it says fundamental, first harmonic, fundamental, second harmonic, third harmonic, and so on. If we wanted to number this, this would be the first harmonic, but it has a special name known as the fundamental. So first we create a frequency that makes a standing wave, but what we would visually see is actually not an entire wave. It is actually half of a wave, because remember, one complete wave cycle has to have both parts of the motion. So this illustration here would only be this part of our wave. So this is actually half of a wave, but this would represent my fundamental, my first harmonic. So then a harmonic series is going to be a series that includes that fundamental and integral multiples of that fundamental. So whole number multiples. So again, if the first harmonic was 6 hertz, then the second would be 12, then the third would be 18, and so on. That is the idea of harmonics. Now, this is how we get our harmonic series in music. They're all multiples of whatever that initial frequency is, okay? Now, if we were trying to calculate what frequencies those different harmonics would be located at, then this is the formula that we would use. So notice it says here waves on a string. Again, this This is what we would see physically on a string. Now, what I want to point out to you is that when we are creating a standing wave on our string, here we are showing you an image where my string is going to be closed off on both sides. So we're going to start with a node and we're going to end with a node on our standing wave. So in order to create that first harmonic, remember, it was actually only half of a wave. And so when we look at our formula over here on the right, you can see that it's only going to be half of a wave that fits on the full length of the string. So if the length needed to make this half wave is L, then in order to make the full wave, I would need 2 lengths of that string. And so that's why my equation says 2L in my denominator when we are trying to find the frequency of that very first harmonic. Now, as we continue to look over the illustration, we can see that at the second harmonic, we end up with 2 half waves or 1 complete wave. And so now, instead of needing 2 lengths of the string, we would need only 1 length of the string. And then as we continue to add additional harmonics to our standing wave, we would find now that we need 2/3 of the string, and then we would only need half of the string, or maybe you could say 2/4 of the string. So with this increasing frequency, we see a decrease in the wavelength. So frequency and wavelength are inversely related, okay? As I increase the frequency by default, then my wavelength is going to decrease. So this is the formula that we would use in order to calculate the necessary frequency to find the first, second, third, or whichever harmonic in our series, where N represents which harmonic. So for this first illustration, we would input an N value of 1. For the second harmonic, this N value would be a 2. For the third harmonic, this N value would be a 3, and so on. If we are trying to calculate or determine the frequency for a series of harmonics when we are manipulating an air tunnel or something, an air column or something like that, well, our image is going to look a little different because we are no longer going to have 2 closed ends. And so we are going to then need to change up how we calculate that frequency for whichever harmonic within our series, because now instead of starting with a node and ending with a node, we're going to start with a node and we're going to end with an antinode. So you can see here that it says that if we have one end that is closed and one end that is open, then we are going to use this equation for our frequency. And then if you'll notice, we can only use this for odd integers of our harmonics. So here is a quick little visual for you. If we have a tube where it is closed on one end, so we start with a node, but it is open on the other, we're going to end with an antinode. So my first harmonic is actually not going to be that little wave bubble that we started off with on the previous image. Now, instead of being, and let me just remind you, this is what our this is what our standing wave looks like, right? So instead of showing this much of a wave for the first harmonic or for that fundamental, if you look, it's only the first node and the first antinode. So my full wavelength would be from here to here. So this is only 1/4 of a wave. And so that's what they are showing you right here in this illustration. So as we continue, the second fourth of a wave would put us here where it ends in a node, but it's open on the back end, so I cannot end with a node. So I will not be able to calculate that harmonic where my N is 2 because it doesn't exist within this air tube, because the air tube is open. The next wave, the next standing wave that I'm actually going to create inside of the air tube has to be where the next antinode is. So if you'll notice, this is the image that we see in the next illustration. We have to fit 3/4 of our wave here. Now there's another 1/4 of a wave. So we have to fit 3/4 of a wave into this tube before we can actually accomplish our next standing wave. So when we go back and look at this equation, that's why it says the n values can only be odd numbers. So 1, 3, 5, 7, and so on. I will upload an additional video to explain, but here I have gone through an illustration of how those different standing waves are created. So I've gone through the different harmonics. Here we have a situation where our system is closed on both ends. So this would be like the string that was oscillated in the classroom in order to create that physical standing wave. And then here is an illustration where I take you through how our standing wave would be created in an open-ended situation, like an air column where we have sound oscillating inside of a tube. So there is a separate video that is uploaded walking you through how all of these relationships were set up